inicio nuestro seminario, que es doble por dos motivos. Primero, porque vamos a tener dos speakers, Javier Maass y Ari Boltzmann, los dos exalumnos del DIN. Y por otro lado, este es un seminario conjunto de probabilidades con un nuevo ciclo o tipo de seminario que estamos lanzando, que es sobre matemáticas e inteligencia artificial, que está partiendo de a poco y vamos a ir agarrando momentum, espero pronto, y ya es el próximo semestre tenerlo implementado sistematico. Entonces ahora vamos a cambiar a English. So our first speaker is Javier Maass. He's going to speak about symmetries in overparametrized networks. Please, Javier. Thank you.
So I'm just going to try to if I can use the laser pointer. Okay. Okay. Hello, everybody. I hope you're doing very well. I'm Javier Maass, as Joaquin said, and I'm going to present you our work titled Symmetries in Overparametrized Neural Networks, a mean-field view that we turned into a paper with Joaquin here. This was my thesis work, my master's thesis, and we turned into a paper that's going to be presented at NeurIPS this year. So the main goal of our work was to basically understand how neural networks can, generalize using a framework, a mathematical framework known as mean-field theory, that allows us to, understand neural networks from a mathematical point of view. But also, we want to mix this theory with existing knowledge about how you can leverage symmetries on a learning problem to try to make your models better. So that's the overarching story of our paper. Now, I'm going to go over different elements that will allow me to explain this. First, I'm going to give you some context of what I mean about when I talk about mean-field theory and how it helps us generalize the problem. Also, what we mean about having symmetry in your data, and then we're going to go on to discuss our main results and some numerical experiments with it to validate them. So, in terms of context, I'm going to just set the setting we were working here. We have, basically, we consider three spaces. Imagine you have a space which will contain features. I mean, this is really learning theory terminology, but I don't know if you get what features and labels and parameters are if you're not familiar with the topic, but basically you have three spaces and you have data that appears following a given data distribution, which is given by this pi here. And this basically tells you that you have some probability of seeing at any given time a given pair of a feature, maybe like a photo of a dog, and a label associated to that feature, which is, in this case, the position of the nose of the dog. Usually people see this, but you have some function that for any feature you have, it gives you the label it should have. But in general, the most general way of seeing this data is by a joint probability distribution. So we will also consider a convex loss function that I'll detail what we'll use it for later, and some activation function, which I call sigma star. And basically, this is different to what people usually refer to as an activation function in neural networks, which, in this case, you just have a function that allows you to mix an input feature with some parameter and give you a prediction of the label that, this associated to this data, what label should be associated to. So we will define a really general and canonical way of seeing a neural network, a shallow neural network in particular, which is you can imagine a neural network as if it was just a combination or an average of n evaluations of the input feature you're getting with a set of n parameters that you then average over. So that's basically this expression that's written here. But in a way, you can see it as you having n hidden units inside your network, that each of them is evaluating your input according to some parameter, and then all those inputs, all those outputs are accumulated to give you the result of your model. And that you can see it as an integration against the empirical measure related to the parameter, or simply written, you can see a shallow neural network model as an integral of sigma star against some empirical measure of parameters. And given that we're writing it like that, maybe you can even see some general idea of a shallow model for a learning problem as being some integral of this activation or unit function against some probability measure, which they live in some space called barren spaces, but that's not really the key here. The key is that even though this seems really general and abstract, what you can do at the end of the day is you can write a traditional shallow neural network, which has just one hidden, you have an input layer, a hidden layer, and an output layer. This this can be modeled using this framework I've just described, in which you define your sigma star to be some specific form of a combination of a linear layer followed by an activation function followed by another linear layer. This is the traditional setting of a single layer hidden layer neural network, and it can be written, and it perfectly maps. If you take these matrices and you write them by blocks and everything, you get exactly the same idea of having n units evaluating your input feature. So that's why we say that this model represents shallow neural networks. But if you notice, this model with an integral against the activation function can go way beyond what I've just described. So having seen this, I'm gonna tell you what we're trying to do with these models. So we have a set of models that we're considering, and we want to learn from data. So what we're seeing all the time are pairs x, y of some feature and the associated label, and we want to use our model to predict what the label should be for a given feature that we're getting. So then, once we make a prediction with our model, we compare that using the convex laws I just mentioned, and then we try to get a model that would work well in most situations. For any pair x, y that you could see appearing, you would like this to work generally well. So for that, you want to minimize what's called what we refer to as the population risk. The population risk basically is what you want to get to in order for your model to generalize well over any sample of your data. The thing is, well, first of all, this risk is really non-convex. As you try to optimize this function based on the parameter, this has a really complex optimization landscape that is really hard to grasp. But furthermore, the real problem here is that we don't really know pi, the real distribution of the data. So in practice, we cannot really optimize this. We cannot really optimize this because we only see samples of the data, not the whole data. Not the whole data distribution. So what people do to solve this problem in practice is that they don't care for optimizing the population risk. They just optimize the neural networks using data, but following this dynamic, which is called an SGD dynamic of following stochastic gradient descent, which is basically you receive your samples like one at a time, and you assume that the result you're getting from evaluating, forget that expectation up there, and just see that loss being evaluated on every single sample on xk, yk. So for every sample, you evaluate it, and then you update your parameter, trying to minimize the loss for that specific sample. So for each given sample, you're basically it's stochastic because you're never truly seeing the functional you're minimizing, but you are using your sample to try to optimize it approximately by updating it based on each given sample. Now, you can see that I highlighted two terms there because they are not, they come nowhere from the loss I've just presented up there, but these are terms that are usually included in the optimization to achieve better results. For instance, when you're optimizing and you try to minimize the population risk, you would like your parameters not to blow up because that would, it could become less computationally. So you usually add a penalization term to avoid your parameters getting too big. And on the other hand, you usually, given that your optimization is already stochastic, you're not really optimizing your functional, why not add some more noise to this iteration? So to your SGD iteration, you usually add some regularizing noise that will allow us to get better guarantees because you're exploring more parts of the space if you want by adding that. So, okay, we can use SGD to try to optimize the population risk. And at least theoretically, it helps to forget about the problem of optimizing in terms of the parameter. We can actually convexify our problem by seeing it as a problem over the space of probability measures. And instead of trying to find the best set of parameters that gives us the best model, why not try to find the best probability measure that achieve this? And in that case, why not see the SGD process as really a dynamic of the empirical measures of parameters over time? So that's where mean field theory actually allows us to understand why neural networks generalize well, because a key result from mean field theory is that when you properly rescale this training process, this SGD training process, and you make n go to infinity, meaning that you make your models be arbitrarily wide, and at the same time you observe this SGD training dynamic every more and more steps, if you want, like every n steps, you're watching your SGD dynamic. Well, that stochastic process actually it converges in some sense to the Wasserstein gradient flow of some version of the population risk, which is this R tau beta that I've noted there. And this version of the population risk is basically the same population risk, but also including, the penalization term I mentioned before. And the fact that you included noise in the dynamic makes it so that an entropy term appears in this, the functional you're trying to optimize by doing the SGD iteration in some way is just a regularized version of the population risk. And this regularization actually, this tau and beta, I didn't say it before, but they can be zero. I could forget about these terms and just optimize SGD normally, and this convergence would still hold. The thing with having the entropy is that it would give us good properties for a Wasserstein gradient flow. And if you don't know what a Wasserstein gradient flow is, it's basically some dynamic, so flow of probability measures. Like it's, if you want like the empirical measure or this asymptotic empirical measure that you get from your training process, will be in some way following the negative of the gradient of the population risk. Even though this functional is defined over the space of probability measures, this like flow of measures is in some way trying to minimize it. Though it's more complex than that, and actually Wasserstein gradient flows don't necessarily achieve the minimum even if R is convex. But well, when you have these regularization parameters that I mentioned before, you can get guarantees of convergence to the optimum of this regularized functional. So all of this is to say that mean field theory allows you to approximate the training dynamic. To see the training dynamic as what it really is, asymptotically in some way, which is trying to optimize the functional we're really interested in. So, and as I said, this functional encodes generalization power. So in some way, you're understanding why your models are generalizing those.
So sorry, so the beta, what was the role it was playing?
The role that beta is playing is that when it's on, if you want, when it's positive, this entropy term, you're optimizing this regularized risk with the entropy term, and the entropy term makes this strictly convex.
Yes, and but in the stochastic gradient descent.
It's just it just appears as you either light up or not the inclusion of a Gaussian noise in your iteration.
So okay, can you make it go to zero as?
If you
with time.
You could, not in this setting at least, but you could in principle, and naturally there are results in which people have proven that when you make tau and beta go to zero, this like the minima of this regularized functional kind of in some, I think like it gamma converges in some way. There's some sort of convergence to the real optima of the real population risk. So yeah, you're not really optimizing the population risk if tau and beta are positive, but you get better theoretical properties if you want. So that's about mean field theory. Now, what do I mean when I talk about having symmetries in your data? Well, imagine again the photos of the dog. You may, when you see this photo, it doesn't matter in which orientation you get it in, you will always know that there's a dog in the picture. And that's basically what we want to encode in our models. If you want to find the position of the nose of the dog, for instance, you would like it to be so that if you predict the nose to be at some position for any given orientation, if you rotate your photo, you would like your prediction to rotate accordingly. Basically, what I just described is what we want our models to satisfy, for them to be equivariant, meaning that if I transform the input of the model, then I want the output to be transformed in some sort of equivalent way. So that instead of basically, if I evaluate the model normally, and if I rotate the photo, I would get the rotated prediction. That is a property that you would expect to have if you have a model. You may have models that predict the position of the nose of the dog, and then those satisfy this. That wouldn't be desirable if you know your data to have symmetry. And what I mean by our data having symmetry, as I mentioned, we are only seeing pairs of data, x, y, given by some distribution pi. So what I mean by saying that our data might be symmetric is that any orientation of the data, if you want, like any rotation of this of these pairs, if you want, of these random variables, should have the same law. You should, in some way, you should expect to see pictures in any given orientation when you sample from this distribution. So really, the symmetry is encoded in your data itself. So when you have symmetric data, you may want to say, okay, now I want to train a model that is equivariant, that actually respects this symmetry in some way. So you have many techniques for doing so. what we call symmetry-leveraging techniques. And the most common one is using data augmentation, which is basically when you're training your model, you're seeing samples. I mean, when you get a random sample from your data, what you do is you randomly rotate it or apply some random transformation to it, or many random transformations to it. What you're just doing is augmenting the pool of data that you have. So instead of receiving just one picture, you receive all the possible orientations. You evaluate what your model would give for any of these possible orientations, and then you apply the loss at that level. So compare how every single different orientation is comparing to the rotation of its corresponding label. So what you're doing here is actually optimizing this symmetrized functional, but in practice, you're not really constraining the model. You're just training it to be, you're just training it to try to induce it to be symmetric. On the other hand, like a close cousin of this technique is feature averaging, in which you actually, instead of, I mean, you actually take your input layer feature that you get, you augment it to all possible possibilities if you want, you evaluate your model, and then you try to put all that back into a single given orientation. Let's say if your dog came, oriented upright, you transform it, you pass it to the model, and then you make all the pictures go back to being upright, so that you can average that prediction and get, a prediction from what we call a symmetrized model. So you're actually taking your model and transforming it and making it so that it evaluates all the possibilities, and that way you're encoding symmetry to the model. So it's slightly different. I mean, just you're integrating before or after the loss, but it makes it makes a difference in practice, but as we'll see, in theory, it doesn't really matter whether you use one or the other. The other technique that's gotten really popular recently is using equivariant architectures, which are when you have neural networks, you usually have one layer after the other. And what you're trying to encode here is to say that every layer has to satisfy this equivariance property. I mean, every layer has to respect the symmetry as you want it to. So this is quite hard to encode in a setting which was really general and doesn't really have any hidden layers. So I'm going to just show you that what you need to do in order for this to happen is to encode the fact that, for instance, if you want your matrices that are multiplying your input to respect symmetry from, going from one layer to the next, what you need to have is some action of the group not over the input or the output space, but on the parameter space. You need to act on, how you have to have some group action over these matrices such that you can encode the symmetry that is this, passing from one layer to the next. So that's why we include this property of, the group acting on the parameter space. And that's why also you need a property of sigma star being jointly equivariant, which is this property that's written down there. But that's not really, it may seem constraining, but it's not really as constraining as you may imagine. Many models do satisfy this without them encoding any symmetry in their architecture, by the way. So the proper way to encode this equivariant architecture idea into our shallow model is to consider a space of fixed points of parameters that are fixed under this group action. And this actually is the proper way of encoding equivariant architectures for, CNNs or DNNs. I mean, CNNs, or let's say, deep sets, for instance, are, neural networks on which each layer satisfies the fact that it is, each linear layer is equivariant, or it's not affected by the permutation of your input coordinates. So in order to have that on a matrix, you need to have a matrix that, shares its whole diagonal and its anti-diagonal terms. So, I mean, this picture is just showing that there's a fixed way of sharing your parameters within the layer so that you will respect the symmetry that you're expected to satisfy. And that, having some parameter sharing, is what's encoded in this subspace EG. So basically what we're doing here is we have some action of our group over the parameters, and we're trying to find, a subspace which encodes the fact that you may have or not an equivariant architecture. You actually have good properties for this space. I mean, this is a linear subspace on the one hand, and you have an explicit projection onto it. So in some way, when you're doing equivariant architectures, you're trying to optimize the population risk, but of a projected version of any model that you may have. So these are like the main concepts that will come into play now for our main results. How much time do I have left? Just to know. Okay, so for our main results, I just told you, okay, we have equivariant architectures on the one hand, and we have other symmetry leveraging techniques. We now want to encode them, or now we want to understand all these concepts in terms of the mean field theory. So as you might remember, our shallow models are given by integrals of the activation against some measure mu defined over the parameter space. So it seems relevant to define or to understand that there are subspaces of this space of measures of probability measures that encode symmetry in some way. And actually, we have two different ones. So for equivariant architectures, you may consider all measures that are concentrated, which have all their weight on this subspace of equivariant parameters, because all those measures will be such that you will have this property of all your parameters being within the space of equivariant architectures. So that's an important space. That's the PEG over here. But you can actually encode symmetry in a more general way, which is through the push forward against the group action. And that's how you get the space of symmetric measures, which is this PG of Z, which basically, I mean, you can turn mu into it to be part of any of these two spaces whenever you want. But the thing is, you have two different notions of symmetry, one being stronger than the other in some way. And that's why we defined what we call weakly invariant measures to be those that live in this space of symmetric measures, and strongly invariant to be those that live within the space of concentrated measures on a given subspace. And actually, when you try to symmetrize, I mean, when going back to feature averaging, when you have a model and you want to turn it into a symmetric model, actually what you're doing when you're working with shallow models is you're actually just symmetrizing the measure. So if your model was given by some given measure, then its closest symmetric version is given by the symmetrization of the same measure. And just with a simple example, you may be able to see this. I mean, the difference between these concepts better. So when you have R and the group of multiplying by -1 or plus or -1 at the action, then the only points which are equivariant, like equivariant architectures for this parameter space, would be just 0, because it's the only point that stays fixed under this action. But if you want to see, you may have a symmetric measure which is not fully concentrated on 0, which is just the average. I mean, if you take some delta set, some measure like put at some point Z, then if you take also its inverse and you have like the measure that averages both things, that is a symmetric measure which is not fully concentrated on this space of equivariant architectures. So you can have symmetric models without necessarily having all the parameters being inside there. That is, you don't need to have an equivariant architecture to have an equivariant model, which is something that, well, people mostly know, but it's just an interesting insight just from watching the theory. So now for our main results, we need to assume some properties of our data distribution. Mildly is just assuming that their moments are controlled. You need to have a convex loss, and for it to be jointly invariant in a sense that your loss is not really affected by the orientation of the labels. And also that your activation function must satisfy this property of being jointly equivariant, which, as I mentioned, is not really that hard to have. Now, the rest of the hypotheses are really there because they are simplifying assumptions so that we don't have to worry about all the well-definedness of everything in our problem, but they are usually, a lot of people are working on lifting these assumptions for working with different kinds of activations and whatever. So as with our population risk, we can understand data augmentation, feature averaging, and equivariant architectures in terms of the population risk, but also in terms of a convex population risk defined over probability measures. And in particular, like one thing we did is we understood that all these concepts actually go back to just the normal population risk and some operation that I just mentioned before, like projecting the measure or symmetrizing the measure or just symmetrizing the population risk itself. So that is an interesting thing. And what you actually get is that when your data itself is equivariant in the sense that I mentioned before, I mean, when your data respects symmetry, then your functional, your population risk functional is symmetric in the sense that you expect it to be. And similarly for, all these functionals here are all invariant. And also when R is invariant, like when your original population risk is invariant, it's also equal to that of data augmentation. So this may seem like kind of weird, but in short, the big thing here is that using feature averaging or data augmentation over the whole space, if you try to optimize using any of these two techniques, the best you can do is actually just as good as optimizing your original population risk only over symmetric measures, which is to say, in a way, when you're using data augmentation or feature averaging, you're constraining yourself. I mean, you won't ever be able to optimize your population risk unless it is also symmetric. I mean, unless it has an optimum which is symmetric, you won't be able to optimize it, because when you're optimizing with these two techniques, you can't get out of this PG of Z. So that's more or less what this figure is showing. And actually, this has a nice corollary. When you're working with a quadratic loss, what usually happens in the learning problem is that you're approximating, I mean, you're finding the model that best approximates the conditional expectation of your distribution, which is this F star here. But when you're optimizing only over symmetric measures, what you get is that you're actually optimizing for the symmetrized version of the conditional expectation. So if your problem, I mean, if your conditional expectation is not symmetric, if your problem does not have symmetric data, you won't ever reach the, I mean, what the best you can do optimizing only over the subset is to approximate the symmetrized version of your conditional expectation, and not the conditional expectation itself, unless you have symmetry in your data. And well, the other consequence is that when you have symmetry in your data, using data augmentation or feature averaging has no advantage in terms, at least of the optimization problem, no advantage at all over, you know, just doing nothing. Just you have your equivariant data, just take advantage of it, and it shouldn't make no. I mean, you have your equivariant data and just train without using any technique, you would get most. I mean, if you approximate well, then you should get more or less the same result. Unfortunately, the same isn't true for equivariant architectures themselves, because equivariant architectures actually, they're really arbitrary in a way. I mean, I just define some action on the parameters and some activation function sigma star. But if I want, I can make this pathological. I mean, not pathologically. I can make a really simple example with all the best conditions that you could imagine, in which still this space EG is really just zero or too constrained in order for it to be, for any model constructed with measures on this space to be really poor. So the thing is, you may get under some pathological conditions, if you want, you won't ever be able to optimize the population risk using only models concentrated on this subspace. But when you have universality of this subspace, which is something that you actually get from many known models like CNNs or DNNs, it's been proven that these models which are concentrated on this equivariant subspace are dense on the space of equivariant functions. So when you have that property, you actually can optimize and you can get the best possible results when you have a quadratic loss, at least, using only these equivariant measures. So having seen how they relate, these things relate in terms of their optima, now we are interested actually in using mean field theory to its full and trying to understand why or how the symmetries translate into the training dynamics of neural networks. So one general result we proved was that whenever you're the functional, I mean, you have any functional over probability measures, whenever it is invariant in the sense that it respects the symmetry of, you know, this in this measure space, then if it has a well-defined Wasserstein gradient flow, then this Wasserstein gradient flow will always respect the symmetries of the problem. I mean, if you start with a symmetric measure, it will always respect it all the way, and it will never stop being symmetric in some way. So that's it's really natural. I mean, if your functional is invariant, then you expect its gradient to respect symmetry also in a way. So if you're following the gradient of this functional, then well, naturally all the measures that you get from that should also respect the symmetry. And this applies particularly to a learning scenario. So let's say we have, you know, a neural network being trained and such that your data, for instance, is invariant. Then you have this respect. I mean, you may initialize your, I mean, this first condition is really easy. You may initialize your parameters all being, I don't know, Gaussian and independent, which will always satisfy the symmetry against, because our group is acting orthogonally. So you will always satisfy this condition. It's really easy to satisfy. But then this says that as you go on with training, you will never stop being symmetric in some way. So that is really interesting. And in this case, at least when you have equivariant data, you can actually reach the optimum of your functional only being, I mean, while still being only symmetric. So actually, when you have beta bigger than 0 and you can converge to the global optimum of the regularized functional, well, you're actually, the optimum to which you're converging is also like symmetric in the same way, which is also kind of natural. The other thing is that we noticed that actually data augmentation and feature averaging don't have any difference even in terms of the training dynamic. So if you initialize both just having some symmetric measure at the beginning and you let the flow go, you make the training dynamic evolve, then you actually get no difference in the actual path that these training dynamics are taking. So even though they seem different to be different techniques, in the end they are just doing basically exactly the same thing. And well, this might sound natural because we're considering a weak notion of symmetry. I mean, we have weakly invariant measures which are being preserved over training, but actually we can make this result even stronger to work even for strongly invariant measures. Now for this, you cannot use the typical training dynamic because if you had a Gaussian noise that is allowed to go anywhere, then you're never gonna stay within a strict linear subspace of your space. So what you need in that case is to project just the noise. I mean, the SGD dynamic is exactly the same. Only if you want to add noise, which as I said is completely optional, but if you want to add it, then you have to project that noise because if not, it's gonna take your flow away from the space that you're interested in. So this doesn't affect the noiseless dynamic, but when you actually take the limit, the scaling limit of this process, you get the Wasserstein gradient flow to a different functional, which is actually regularized, but with a variation of the entropy term, which is not quite the same as before. But it doesn't matter, because what you're actually interested in is in this dynamic here. And what you get is that if you initialize your dynamic to be fully concentrated on this, I mean, fully strongly invariant, like concentrated on the subspace of equivariant parameters, what you get by the end is that this dynamic will always stay within this space, and it will never leave it, even if you're not sure to find a minimum within this subspace. I mean, as I mentioned before, this PEG might be really poor and might not actually get to the minimum of the population risk. But when you have symmetries in your data and you start in this subspace, you're condemned to never leave it, at least on the mean field scaling. And this works even if you're not doing any symmetry leveraging techniques. So you just have symmetric data, and you train using this symmetric data, and you start, for instance, it's really easy to start being concentrated on this subspace. You may start just with all your parameters being 0. Well, then you're actually doomed to never leaving this space as long as your data has the symmetry that you want. So that is interesting. I mean, you're either doomed or, well, as we'll see later, this is also an opportunity to try to discover how to make more parameter efficient architectures that respect symmetry. So, and well, this works for like the normal population risk where your data is symmetric, but it also works if you replace the population risk with data augmentation. So you don't even need your data to be symmetric. I mean, what this is also saying is that if your data is not symmetric, but you use data augmentation and you initialize your training within this subspace, well, you will also never leave it, even though you could. And well, the other result is that all these techniques are the same. I mean, all these flows actually exactly coincide once you initialize them all to be on the same measure, for instance. So all these results may seem, I don't know if abstract, or I don't know if you directly get the hold of them, but I find that the numerical experiments we did are really enlightening for that regard. So what we did was just as a proof of concept. I mean, these experiments are far from being the real application scenario of neural networks, but just we took some toy example of having our features being 2D vectors, our labels to be 2D vectors, and our parameters to be just 2x2 matrices, and where the symmetry is applied by permuting the coordinates of these vectors. So in a way, what we're only doing here is we're trying to study whether with this simple example, and when data is generated by just sampling a Gaussian distribution and passing it through a neural network for which we know the parameters, we want to see if we then train a student model, like just another neural network with a lot of particles. We wanted to see if it would approach or not the teacher model, which is something you could expect, but also how it would behave in regards to the results we proved. So first, I can show you this I don't know. Well, maybe I'll show this figure first because I find it really compelling. But what we were doing here is you have these squares which are the teacher particles. I mean, you have a neural network that's generating your data that's given by the parameters which are given by these squares on the image. Now, this when you're training your student models, we are here initializing them all to be strongly invariant. So that means all parameters started within the subspace. The thing is, when you train it with an arbitrary teacher, these parameters, I mean, these student parameters, which are the little dots, actually escape this subspace and try to approximate the teacher to the best way possible, which is the natural thing to do. But when you use data augmentation, even though you're not really constraining the parameters to stay there, I mean, they could really just update and leave the space. They actually stay there because you're training them with a symmetry leveraging technique. So that's more or less what's happening, and that's what these figures show, actually. So when you have an arbitrary teacher, your vanilla training just leaves the space. I mean, it never. In this first figure, I'm showing whether the particles are staying or not within the subspace. I'm measuring how far the empirical measure of these parameters are to staying in the subspace they were initialized in. When you have vanilla training, it always leaves this space, and it never approaches either data augmentation or feature averaging. But what you do have is that feature averaging and data augmentation are really close to each other. But once you have symmetry in your data, then vanilla training, actually, when n starts growing bigger, it starts approaching what we mentioned in our theorems. Like vanilla training, just without any symmetry leveraging technique, starts looking really like that, just using data augmentation or feature averaging without it being explicitly told to do so. So actually, here we're comparing. Okay, so this dynamic is staying more and more in this subspace, and it's actually looking more and more like data augmentation and feature averaging, which both of them look really similar to each other all the time. So that's when you initialize this to be concentrated in the subspace. And as I mentioned before, when you don't have symmetry in your data, you leave the space. But when you do have symmetry, I mean, this is exactly what it looks like when you're training just vanilla, but with a symmetric data set as well. So that's also a corollary from our theory. I mean, training with an arbitrary teacher with data augmentation is the same as training with vanilla particles, but with a symmetric teacher. So that's more or less what I can say about the strongly invariant results, which I find really interesting and really unexpected. I mean, as I said, here all the particles are outside this plane. You would expect the model to try to go outside the space, but it doesn't because you have symmetry. For weakly invariant, I mean, when you initialize your particles to be weakly invariant, you get more or less the same results, but less with a less compelling case than before, in the sense that here you need n to be very large to start seeing this, but mostly because before, when you were sampling a distribution which is concentrated on the subspace, the empirical distribution you get is also concentrated here. But when you're sampling for just a symmetric measure, for instance, a Gaussian distribution, the empirical measure needs not to be explicitly symmetric. So you actually need to have a larger n to see this initial and final distribution being completely symmetric, as well as for data augmentation and feature averaging to start looking like each other, you need to have larger n. And when you have a weakly invariant teacher, well, vanilla training also starts approaching both data augmentation and feature averaging. So the results we mentioned before all start to show in practice, actually. So that I find to be very interesting. Finally, we devised something because of this, figure of, particles escaping the space that they aren't supposed to be in. We devised an idea to how you could use this. I mean, unfortunately, we don't have theoretical guarantees for this heuristic. But we devised an heuristic in which you could try to discover the symmetries of your problem based on this fact that student particles may be leaving the space you're interested in. So, for instance, say you want to initialize your student models, or you want to initialize your model to be just concentrated with all parameters concentrated in 0. So that way you ensure that you're always initializing to be strongly invariant in some way. And then you train and you see whether you left that space or not. In this case, this particles left the subspace they were initialized in. So that subspace couldn't have been EG, because if they had been initialized in EG, they wouldn't have left it because of the theorem 5, if I recall well. So what you do is you notice that, okay, you escaped your initial space, then maybe you can add this new direction that you discovered to your initial subspace, and then initialize a new neural network completely contained here, and train it and see whether it leaves this initial line you're drawing or not. In this case, it is leaving it. I mean, you're after training, you do leave the line you initialized on, but you discover a new direction which could be useful for which now could, for instance, not which can help you build this new space. And actually, if you see here, once you draw the new direction here, you had one line which was this one, and now you're adding like a perpendicular one. You're actually, the next step to this this dynamic is to initialize it being wholly contained in the equivariant subspace, and after training it will remain like that. So what you expect to see is eventually this algorithm, I mean this heuristic, if it's true that you always leave the spaces that you're not supposed to be in, then you would eventually converge to get to the largest possible subspace, which allows to have strongly invariant architectures. And this could be potentially useful for people trying to discover optimal architectures for, or discovering the symmetries of a problem in some way. So this is one of the ideas that came after doing our experiments and experimenting with our results. So just to wrap it up, conclusions of our work are that symmetry leveraging techniques can be expressed in mean-field terms, and we can use mean-field theory to understand them and to understand that symmetries are respected even in a really strong way. That data augmentation and feature averaging are actually not, in the mean-field limit at least, they are not that different from each other, and that you don't get much from using either of them whenever your data is already symmetric, and that all these results could be validated empirically. And so for the future, we want to try to quantify then what is the real advantage of using either data augmentation or feature averaging, because there must be some advantage. I mean, if people are using them, then maybe what they allow for you is to converge quickly to the mean-field regime, for instance. I mean, you get quicker to being approximately like your gradient flow, for instance. Also, we want to extend our analysis to a wider range of architectures and provide both theoretical guarantees for a heuristic and a more wide and really more realistic experimental setting to see whether our results hold in practice, but in more realistic settings with training with images or any kind of other kind of data. So having said all that, I thank you very much for your attention, and I am here for any questions if you have them.
Thank you very much, Javier. Question for you. Yes.
I have a question regarding the teacher-student setup.
Yeah.
So the teacher network learns from the generated data.
The student network is learning from generated data, and the data is generated by the teacher model. So the teacher model is just the model which is given by the particles, which are these squares here. So imagine like each point in this space represents a parameter of a neural network. So the teacher model is a neural network which is built with these 5 parameters, which are these 5 squares here. And then you use that model, which is fixed and you know it beforehand, to train a student model. So you generate your data pairs using X and your teacher model, and then we used SGD or data augmentation or feature averaging to train a new, completely refined, a completely new model, in this case with 1,000 particles, which are these 1,000 points which are in the space. And this model is trying to learn it's trying to learn to best approximate the results of the teacher.
So the teacher model isn't trained.
No, teacher model is just,
you just set the parameters.
Yeah, we set the parameters, and then we try to see whether the student that is learning from the teacher is approximating the teacher or not. And it may be doing so in terms of loss, but at least in terms of particles, here you can see that at least when you train with data augmentation, you're not approximating the particles at all. You're staying within the subspace. I mean, maybe you're approximating them within the subspace, but you're not leaving the subspace to actually try to approach them, as is the case for the vanilla model. So that's more or less what's happening.
Thank you.
When you say there is rotations, you apply rotations to the images or the matrices.
Yeah.
In the way you generate to keep the invariance. But can this be generalized to any kind of rotation, any kind of transformation?
That's another one of the open questions we have yet to tackle. I mean, it's one really interesting thing, because here we're working with a really specific kind of symmetry, which are, first of all, generated by a group, so you can invert your transformation, so you can rotate it and rotate it back. And it's also, we're assuming that a group is compact, so you have a Haar measure which is normalized and allows us to make all these symmetrization operators and all that. So you have both of those things, and in particular, they are acting on your space orthogonally. So you're acting in a linear way as well. So it's a really specific set of symmetries, which is quite general enough to tackle, you know, like the symmetric group or, you know, any finite group. It is usually good enough. But as you mentioned, maybe you would want to have data augmentation where you're corrupting your images. So you have an image of a dog, and you want to turn it into a noisy image of a dog. So that transformation isn't necessarily invertible. So there you start having problems with the mere fact that this is a group. But that's one of the directions we want to go on. And actually, I find this heuristic to be really interesting in that specific case, because maybe you manage to generalize this to transformations that are not invertible, then maybe you could, instead of doing a lot of data augmentation to try to, you know, corrupt images or whatnot, maybe you could create a model that in some sort of way is robust to that kind of corruption as well. Because here you're finding a space EG which respects the symmetry that you're interested in. So maybe you could do the same with, you know, other kinds of augmentation which aren't necessarily given by groups. But I find that to be an interesting future path as well.
Good, thanks. Yeah. Otherwise, I think Pablo, you want to have a question? You need to turn your microphone.
Sorry. Hi, Javier. How are you? I have two questions. So first of all, what do you mean by universality on that hypothesis on the measure? Can you go back, please, on that point?
Okay, so I started just this one first. So universality is basically, I mean, it's a fancy way from, you know, AI terminology to say that it's dense. Okay, so you can approximate any function with it. So you need.
Okay. Perfect. And the other question is like, can you elaborate a bit on the proof of theorem 3? Is it like which kind of techniques do you use, or is it like the proof goes like it is what it is, like?
It's more or less it is what it is. I mean, not a really. I mean, it's quite a natural result, and we actually expect it to hold to many other kinds of dynamics, which we have.
Yeah, right.
If you see here, actually, in your Wasserstein gradient flow, you have the appearance of many things, but one of them is the intrinsic derivative of R. So if R is invariant, you actually prove that this intrinsic derivative is also it's not invariant, but it's equivariant in some way. So it does satisfy your symmetry. To some, I mean, if you input here like the push forward of this measure and the push and the application of the group action on the parameter, I mean, if you apply, how would I say this? Okay, if you can show that mg times mu satisfies the same equation, and since it has a unique solution, you can prove the same as any image through any.
I see. Okay, thank you.
No problem.
Just one comment. Yeah, the other one is more tricky.
Yeah, the other one is more tricky. I mean, this one, I mean, it is natural, but it actually took a long way to, I mean, even to just write this this equivariant thing, like this sigma star being jointly equivariant, this is a really wide generalization of the fact that you might have equivariant architectures. And actually writing it like that, once you write it like this, everything comes out more naturally than if you try to actually implement it for any specific implementation of sigma star. So, and actually the other one is more tricky because you have to use the I mean, you actually have to prove that this dynamic, which is concentrated, I mean, it has to remain concentrated on the subspace. But that's more or less it.
So, I have a question which is not well defined, so I'm going to play the role of Joaquin. So essentially, like if you think about physics, given that you already have a physics Nobel prize in machine learning, so essentially physics is by Emily Noether's idea is just codified by symmetries.
Yeah.
So would there be a way of doing this story to obtain laws of physics? Like you give them physics and you try to do your algorithm that you're not completely sure it exists, and it tells you, okay, so you know the laws of physics are time invariant, so you get the conservation of whatever.
I mean, I don't know if I'm getting the whole question right, but I do know that we've discussed this with Joaquin at some point, that there are some papers trying to apply this to get some sort of Nether's theorem, but for neural networks as well. And that kind of same thing, I think it's not been done for in the mean field case. I mean, it's done for finite neural networks, but maybe the good thing about the mean field approximation is that you get better properties in some way, so it's maybe easier to get that kind of result.
Yes, so it was doing like the opposite, like in the sense of, because in a way you can detect now symmetries that you could not detect. Can you detect laws of physics using neural networks?
Maybe you could. Like I feel like it has something to do with maybe this thing of maybe you're assuming you have some symmetries, but maybe you're discovering that you're breaking the symmetries that you expected to have. So once you break symmetries, maybe you can, I don't know if you can get the laws of physics, but you get maybe understand that there are some things that are not being preserved like you thought were, or some laws that. There.
Okay. Further questions? Okay. So let's thank again Javier. We will have our second talk in like 15 minutes.